In the world of wireless, it really all comes down to the antenna. It's that critical link between our electronics and the airwaves. But as any RF pro knows, antenna design is never about finding one perfect solution. It's really about mastering the art of the trade-off. So in this explainer, we're going to break down those compromises. Just to give you some context, this is part 10 of our big 20-part series for all you RF technicians and engineers out there. Everything we're talking about is based on a really detailed report on radio frequency propagation by the RFI detectives who are part of Virtualization Options LLC. We'll be building on some stuff we've already covered, so let's get right into it. Okay, so here's our game plan. We'll kick things off with the absolute fundamentals, the principle of resonance. Then we'll look at the basic building blocks, your dipoles and monopoles. After that, we dive into what I call the great trade-off, gain versus directionality versus bandwidth. We'll take a tour of some common designs that really show these trade-offs in action. And we'll wrap it all up with a practical guide on how to choose the right antenna for the job. All right, so let's start right at the beginning. Antenna fundamentals. This is really the why behind the wire. What's the one core principle that makes every single antenna work? It all boils down to one word: resonance. The best way to think about it is like tuning a guitar string. When that string has just the right length and tension, it vibrates perfectly at a specific note. Well, an antenna is exactly the same idea. Its physical size is tuned so it can be super efficient at grabbing or sending out a specific frequency of radio waves. And this simple formula right here, it dictates literally everything. The perfect physical length for an antenna is directly locked to the wavelength of the signal. So you can see right there, if you have a lower frequency, you get a longer wavelength, which means you need a bigger antenna to hit that resonant sweet spot. It's a law of physics, you just can't cheat. So here's what's happening on the wire. You feed an alternating current into the antenna, and these electrical waves shoot out to the ends, bounce back, and then they crash into the new waves coming in. When you're at resonance, when that length is just right for the frequency, this crushing of waves creates this beautiful, stable, powerful pattern of energy. That's your standing wave, and that's the magic that launches RF energy out into space so effectively. Okay, so with that principle of resonance in our back pocket, we can look at the two most fundamental designs in the entire RF world, the dipole and the monopole. Pretty much every complex antenna you'll ever see is derived from these two basic concepts in some way. So you've got the half-wave dipole. It's the absolute classic, just two quarter-wavelength pieces of wire fed right in the middle. But the monopole, on the other hand, is kind of like half a dipole. It's a single quarter-wave element, and it cleverly uses a conductive surface, like the metal roof of a car, to act as its other half. That's exactly why those simple whip antennas on vehicles work so well. They're using the whole car as part of the antenna system. And because it's so common and so predictable, the half-wave dipole is really the benchmark. It's the standard that we measure all other antennas against. If you understand the dipole, you've got a solid foundation for all of antenna theory. Okay, now we get to the real heart of antenna engineering, the great trade-off. Every single design choice you make is a balancing act between three critical and usually competing factors. And those three factors are gain, directionality, and bandwidth. Gain is all about how well you can focus your energy. Directionality describes the shape of that focus, and bandwidth is just the range of frequencies the antenna works well on. The big challenge is you can almost never max out all three at once. If you push really hard for high gain, you're probably going to end up with a really narrow bandwidth. It's a constant give and take. And let's be crystal clear about something, because this is a huge misconception. Antenna gain is not amplification. An antenna is a passive component. It doesn't create new energy. The best analogy is a nozzle on a garden hose. You're not creating more water, right? You're just concentrating the flow into a more powerful, focused stream. That's gain. So how do we actually see this focus? We use something called a radiation pattern. The main lobe, that's where all the action is, the direction of maximum power. The side lobes, that's wasted energy going in directions you probably don't want. And the nulls are total dead spots with basically zero signal. The shape of these patterns tells you everything you need to know about an antenna's directional behavior. So how do engineers actually solve this trade-off puzzle in the real world? Let's take a quick tour of a few common designs, and you'll see how each one represents a different kind of solution. First up is the Yagi-Uda. You've definitely seen these on rooftops for old school TV reception. What's so cool is that only one of its elements is actually driven.
hooked up to the cable. All the others are called parasitic. They aren't electrically connected at all. They just sit there and passively shape and focus the radio waves, kind of like lenses for RF. The result? A very directional, high-gain antenna. And the trade-off? You guessed it, a super narrow bandwidth. It's a total specialist.
Now, what if you need to solve the Yagi's narrow bandwidth problem? Well, for that, we have the log periodic antenna. It might look a little similar, but it works in a completely different way. All the elements are driven, and their sizes follow this special self-similar pattern. This allows the antenna to work really well over a huge range of frequencies. The compromise here is that you get more moderate gain in exchange for that giant bandwidth. And this table here, it just lays it all out perfectly. You can see the whole story at a glance. The simple dipole, low gain. The Yagi cranks up the gain but sacrifices bandwidth. A parabolic dish takes that to the absolute extreme with a tiny beam and massive gain. And then the log periodic says, I'll give up some of that gain to get a ton of bandwidth. It's a perfect snapshot of the engineering choices we've been talking about. So all of this brings us to the final, really practical question. How do you actually use this knowledge? How do you match the right tool to the right task?
It's really just a logical process. Step 1, figure out your bandwidth. Are you listening on one specific frequency, or do you need to scan a whole range? Step 2, your coverage area. Do you need to send a signal everywhere, or just from point A to point B? Step 3 is gain. How far does the signal need to go? How strong does it need to be? And finally, you gotta come back to the real world. What are your physical constraints? How big or small can this thing actually be?
And, of course, while we've covered the fundamentals today, we have to be real about it. This quote from the source material really nails it. True, real-world antenna design is an incredibly deep and complex field. It's a mix of physics, material science, and some really heavy-duty computer modeling. So let's end with a question to chew on. With this constant push for our devices to be smaller and to handle wider and wider bandwidths, these fundamental trade-offs don't just go away. If anything, they get even tougher to manage. So what compromises will shape that next generation of antennas? How will new technologies find clever ways to bend these old rules? That's the question that's driving all the new innovation in wireless. Thanks for joining me.